All right, let's continue transforming our sinusoidal functions. To recap our last lesson, what we looked at was the sinusoidal function in the following format, okay, where we looked at what effect did this d value have on our function. We found that it translated our function left or right. And one of the things we realized was that if it says x minus, let's say, 5 here, right? If it says x minus 5, what's really happening is that you're moving your curve 5 units to the right, even though it says minus 5. All right. And then we also looked at this variable here, our c value, and found that it actually moved our equation, moved our curve up or down, depending on the value that's there. So if it was plus 5, it would go up 5, minus 5, our curve would go down 5. And that was true for the cos function as well. And just to recap what our table of values is for the sine function is the following. Okay, remember that the sine function starts at the equation of axis, which is 0 for y equals sine x, goes up to 1, comes back to 0, down to -1, and then back to 0 again. All right, and then we've got the curve of y equals cos of x. The x values are the same, and the y values just vary in a very small way. The only difference is that our cos function actually starts at the maximum of 1, comes down to 0, down to -1, back to 0, and then back to +1. Each situation, one period is, or the length for one cycle is 360 degrees. All right. Now what we're going to be doing is we're going to be adding to this equation. We're going to be adding to it. We are going to add a value in front of sine, and that's going to be represented by the letter A. And we're also going to be adding a letter or a variable in front of our x, which will be represented by the letter k. So what we're going to be looking at is what effect does this value have as well as this value have on our function. All right, so we're adding two more variables to our equation to kind of finish this off with respect to transformations. To do that, we're going to go to Desmos and we're going to do a few investigations, okay? So first thing, if we follow these instructions, we are actually going to look at the effect that the A value has. So we are looking at the following. All right, forget about K, D, and C right now. We're just looking at the effect of having a value in front of our sine function. Okay, so we're going to go to Desmos. We're going to change our window to 0 to 360 degrees, our y-axis from -5 to 5. Okay, so let's do that. And make sure we change to degrees from radians. So let's go into Desmos. And, let's change this up. Let's go from 0 to 360 in degrees. And here we're going to go from -5 to 5. All right. We can move that over just a little bit. Okay, here we go. So let's see which equation we need to graph here. Oh, and 1 second. Let's change one more thing here. Let's do our step. Okay, so our step, this is kind of like our minor grid lines here. Let's do our step by 30 degrees. And then here we'll do our step by ones. Okay, this way we can actually see all the values we need here. All right. Okay, let's go back and let's plot y equals sine x and y equals negative times sine x. All right, let's see what the effect is when we have a negative. And you're going to see that it's going to make total sense what happens. So if we have y equals sine of x, okay, here we are. It's understandable. We have one full cycle from 0 to 360. This is our parent function. Maximum at 1, minimum at -1. our three x-intercepts are there on your screen. Okay, and we're going to plot y equals negative sine of x. So y equals negative function sine of x. Close my bracket. And let's observe what's happened here. Okay, so our base function is in red and our new function is in blue. What does it look like has happened? Well, if I take a quick screenshot here so I can write on this. Okay, let's just write on this quick here. So what has happened? It seems as though our max of 1 has now flipped down to negative 1. Okay, our intercepts are the same. So we still have the exact same intercepts. The only thing is something has occurred where our positive values have now flipped to negative. So this whole section has flipped to the negative side, while this whole section has flipped to the positive side. And what we call this, okay, is a reflection across the x-axis. So there is a reflection across the x-axis. And all that means is that imagine our x-axis is a mirror, all right? Our curve is being mirrored across the x-axis. Okay, so all our positive values have become negative, our negative values have become positive. And that makes sense, right? Like imagine our table of values of x and y equals sine of x, right? We have 0, 90, 180, 270, 360, 0, 1, 0, negative 1, 0. Well, what has happened is now we've multiplied all of these by negative 1, right? Because the negative is now in front of the sine x. So you now have sine x times a negative 1. And so we've essentially multiplied all of these by negative 1, hence changing all their signs. And so what we've done here then is just taken all our y values and multiplied them by negative 1. And you can see that our x values have not been affected. Our x values are staying the same. The only thing that's changing is you're finding sine of x, so you're finding your y and then multiplying it by negative 1. And so all that's changing are your y's. All right, and that's important to note. Okay, that's important. So how do the graphs of y equals sine x and y equals negative times sine x, how do they compare? So if we were to put this into words, the graph of y equals negative sine x is reflected across the x-axis. Okay, so simply taking all your negative values and multiplying them by 1. Okay, so multiply all y values of y equals sine x by negative 1. And if there was a negative 2 in front of sine x, then you would multiply all your y values by negative 2. All right? Let's continue. Okay, so now we know the effect of a negative value out in front of sine or cosine. All right? It flips your graph. It reflects it across the x-axis. Okay? And now we're doing the following two equations. Y equals cos of x and y equals 4 times the cos of x. So back into Desmos, let's erase what we've got. And let's plot, this time, our cos function. Okay? Which we know our cos function starts at a maximum, right? Crosses x-axis, gets to a minimum halfway through, and then back to its maximum, back to its one, after completing one full cycle, it takes 360 degrees before this all starts repeating again. Let's see what happens when we have a 4 times cos x. Any predictions as to what you think might happen? I want you to think about this. You're now going to take all of your y values because it's 4 times whatever you originally got for the sine of x. So think of our original table of values of 0, or in this case, it's the cos function, 1, 0, -1, 0, 1. We're going to take those values now, and now we're multiplying them by 4 because there's a 4 in front of your cos x. So we should see here all our y values getting 4 times larger. Okay? They're getting 4 times larger because we're multiplying 4 times cos of x. Let's see if that happens. Okay? Let's compare. So we've got, take a look. Here, okay, I can't have two points on different curves tapped at the same point there at the same time. But we have 0, 1 became 0, 4. Here, 0, 0 is still, or sorry, 90, 0 is still 90, 0. And then here, our base function was at -1, and now we're at -4. Okay, until we get back to the top here. Why is it that for both of these graphs that our intercepts stayed the same? Why is it that both are 270 times 0? I thought we were multiplying all our y's by 4. Well, our y value in this case is 0. Multiply 4 times 0, and you still get 0. All right? I want to make note of one other thing here. Okay, so I do want to make note of one other thing. And to do that, let's take a look and write down what our amplitude is here. Okay, what is our amplitude? And just give me 1 second. Okay. So what is our amplitude here? It was 1 before. So for y equals sine x, our amplitude equaled 1, right? And now for our new curve, if I do this in a different color, for y equals, sorry, and that should say cos of x. I should definitely erase that. Okay, so for y equals 4 times the cos of x, our amplitude is what now? Let's look at our graph. Remember that the amplitude is the distance from your equation of axis, and in this case our equation of axis is right on the x-axis, that's the middle, to the minimum, or the equation of the x-axis, or the equation of the axis to the maximum. And you always state it as a positive value because it's a measurement. And what you'll find is that your amplitude is 4. Okay, so amplitude is 4. Are we seeing a connection here with the number that was in front of cos of x here and the number that is in front of the cos of x here and what the amplitude is for each? That's right. Hopefully you're seeing that that value there represents, not only is it being multiplied by the y values, it also represents the amplitude. And mathematically, okay, what it's doing to our base equation is it's vertically stretching it. Do you see how it's becoming more elongated? Okay, so the blue curve is becoming more elongated, right? What's happening is that this graph, mathematically speaking, it's getting vertically stretched. That's what you call it. Okay. Not only that, but that value in front of cos of x also represents the amplitude. All right, so we're getting vertically stretched here by what's called a factor of 4, and the amplitude equals 4. Okay, so that's important to note when we go to answer this question here. How do the graphs compare? Okay, so the graphs of y equals 4 times the cos of x has an amplitude of 4, okay, the y values of y equals cos of x are being multiplied by 4. Okay, hopefully that makes sense to you here. They're 4 times larger. Okay, and let's move on now. Now we've done a negative, we've done a number greater than 1, and now we're going to look at a number in between 0 and 1. So what happens when a is in between 0 and 1? Okay, and actually it's not going to equal 0 there, and it's not going to equal 1. It's just going to be either greater than 0 or less than 1. Okay, so what happens in this case? This time we have a 1/2. All right, let's take a look. Okay, y equals function 1/2. Okay, function sine of x, close my bracket. Let's take a look at what happened this time. I think you kind of get the idea here. If before we multiplied our y values by 4, now we're multiplying our y values by 1/2. And so what's happening is now we're not getting a vertical stretch. It's not getting elongated. It's actually getting flattened out. Okay, it's getting flattened out. And so we call this a vertical compression. All right, a vertical compression. If I zoom in a little bit here, okay, so we can see a little bit better. All right, our y-intercepts, as you can see, are still the same. They're still the exact same. It doesn't matter because if where you had a 0 in your parent function, it doesn't matter what you multiply 0 by, you still get 0. But what happens is we went from a maximum of 1 to now a maximum of 0.5. We multiplied by 1/2. All right, and the same happens throughout this curve. Okay, and so what is our new amplitude? If I were to quickly take a look at what our new amplitude is here. Right? Okay, so our new amplitude here now, from the equation of axis to the maximum, amplitude equals 0.5. Whereas before, in the original function, amplitude equaled 1. So once again, whatever number is in front of your sine x, that becomes your new amplitude. That is also called a vertical compression because now we're flattening the curve. It's a vertical compression by a factor of 1/2. All right? Okay. So let's go back to our note and let's finish this off for the effect that a value has on our sinusoidal functions. So how do the graphs of y equals sine x and y equals 1/2 times sine x compare? The graph of y equals 1/2 times sine x has an amplitude of 1/2. The y values, okay, the y values of y equals sine x are multiplied by 1/2. Okay? We also say that there is a vertical compression by a factor of 1/2. Okay? By a factor of 1/2. Okay, and now let's summarize here. We have if A, and notice how there's these brackets, these straight brackets around A. That means take only the magnitude and not look at the sign in front. So it's called the absolute value of A. So if the absolute value of A is greater than 1, so forget about the negative, we'll deal with the negative later. Okay, there is A, or the graph is vertically stretched. Okay, by a factor of A. If it's between 0 and 1, it's vertically compressed. By a factor of A. And if it's less than 0, then it is reflected across the x-axis. Okay, and there you have our effect that A has on our sinusoidal function. Let's now look at the effect of K. So instead of A now, let's assume A is 1. Now we're looking at the effect of K. So having a value out in front of your X. Okay, let's see what happens. So let's plot y equals sine X and y equals sine times 2X. Or sine 2 times X. All right, so let's come back in here. Let's go back home. Oh, don't go back home. Okay, set it back up again. All right. Okay. So now we're going to do y equals sine X. Okay. And we're going to do y equals sine of 2 times X. Now I want you to think about this. When you have sine of 2 times X, so let's say, for example, in the base function, we were plugging in we were finding the sine of 90. Okay, the sine of 90, which would be 1. Now we're doing, when we plug in x of 90, you're multiplying it by 2 first. So you're actually doing the sine of 2 times 90, which becomes 180. So I want you to think about this. What do you think is going to be affected, your x values or your y values? What did you end up multiplying by 2? You multiplied your x value by 2. 2 times 90, right? When you have the function y equals the sine of 2 times x. So you multiplied your x value by 90 in this situation here. Okay? And so let's see what's happened here. We did have a period of 360. The base function is blue. We had a period of 360. Is our period 360 anymore? It seems as though our period now, before we have, and let me take a quick screenshot here. Let's analyze this. Okay. We did have a period of 360 where we had one full cycle until 360. But now it looks like we have, right? We've got 2 full cycles. And so what has happened is, look at this. We went from a full period to 360 to now being 180. So essentially, the period is half the period for y equals sine x. So for y equals sine 2 times x, the period is half the period for y equals sine times x. And that makes sense because everything is happening faster here because you're multiplying it by 2. So instead of, let's say, taking the sine of 90 in our base function, you're actually taking, where normally that would be 1, right? You're actually taking the sine of 2 times 90, which is 180. And so that is why now here you are down at the x-intercept there. So everything is happening faster, okay? And if I were to draw what's happening here, essentially the base function is being vertically or horizontally compressed. It's being pushed together horizontally so that there's more periods in a specific time frame. It's being horizontally compressed. Like, see my arrows that I'm drawing here? It's being horizontally compressed so that the period is happening faster. Okay? So, when our k value is greater than 1, what's really happening is our period, okay, is actually getting shorter. And we're actually compressing, we're horizontally compressing our base function of y equals sine x. Okay, so let's go in and fill in and answer our question. So it says, how do the graphs compare? Well, the graph of y equals sine of 2 times x is compressed horizontally, got squished together, so the period happened faster, horizontally by a factor of 1/2. Now you might be asking, is there a coincidence that this is a 2 and we're compressing by 1/2? The answer is yes. That is not just a coincidence. That is something that will always occur. So let's say that the question was the graph of y equals the sine of 3 times x. That means that we're going to be compressing horizontally by a factor of 1/3. Or if it was sine of 4 times x, it'd be compressed horizontally by a factor of 1/4. The larger the k values, the more compression you're going to get, the faster the periods are going to occur. Okay? What happens when k, the absolute value of k, is between 0 and 1, like in this case? Okay? What's going to happen there? Well, if it's greater than 1, we get a compression. Then you can imagine that if it's between 0 and 1, we're probably going to get a horizontal stretch. But let's take a look. So it's like the opposite of what makes sense, right? Like normally you would think that a number between 0 and 1, that the graph should be compressing, but that's not what occurs here. Okay? It's the opposite. And I've proven to you why that is. So let's keep, and actually we're doing cos of x now, right? So let's go y equals cos x and y equals cos of 1/2 of x. Take a look at what has happened here. I actually have to expand my window here, and I need to expand this out to 720 to see what's really happening, because that's now how long one of my cycles is taking. Let's do a quick screenshot here. Sorry about that. Right? So let's analyze this. This is now our curve of y equals cos of 1/2 times x, whereas this was y equals cos of x, our base function. So you can see here what has happened to our period. Our one period used to be on our base function from 0 to 360, right? That was one period for our base function from there to there. Now for our new function, take a look. What's our period? It's actually going now to 720. So the period of y equals cos 1/2 times x is twice the period of y equals cos times x, or cos of x, sorry. And so what we call this now is a horizontal stretch. This is a horizontal stretch by a factor not of 1/2. What's really happening is we're getting a doubling effect. So a horizontal stretch by a factor of 2. So everything to do with the k value, it's opposite. You are multiplying it by your x's, okay? You are multiplying your base function of the x values of your base function by your k value. And the effect that has on the graph is the opposite of what you think. Okay? If k is greater than 1, then you're actually getting a horizontal compression. If k is in between 0 and 1, then you're getting a horizontal stretch. Okay? Let's answer here. How does the graph compare? How do they compare? The graph of y equals cos of 1/2 times x is stretched horizontally. It got bigger. The period doubled. Stretched horizontally by a factor of 2. So we had a 1/2 here for k, and we got a stretch, vertical stretch by a factor of, horizontal stretch by a factor of 2. And if that number there, our k value was, say, 1/3, we would get a horizontal stretch by a factor of 3. The period would actually triple. If we got a 1/4, the period would actually quadruple. All right, so it continues to horizontally stretch this out. What transformation do you think would happen if we had a negative k value, right? A -1. Well, just like above, remember above there was a reflection across the x-axis. Now there's going to be a reflection across the y-axis, the opposite. Okay? Let's observe that quickly on Desmos before we finish this off. Okay, so I'll just add a new graph here, and I'll do y equals function cos negative x Okay, so for whatever reason, Desmos doesn't want to graph that. Okay. But you can imagine now is you're multiplying your x values by -1 because you're now doing cos of negative of whatever x is. So let's say your x is 90, you're now going to take the cos of -90. Okay. And so what that's going to do is it's going to flip your graph across the y-axis. Okay, it's going to flip your graph across the y-axis. And the reason why it wasn't showing up there is because it would be identical to that one. Okay, that's the reason why it wasn't showing up. It would be identical to what's drawn there. If that was your only transformation, it would look the exact same. Okay, and that makes complete sense. So, all right, you can't see it here, okay, because it's identical to the graph above. Because imagine if I take a screenshot. Let's take a quick screenshot so we can realize why we actually don't see any new curve there. Okay, it makes total sense. If it's reflected across the y-axis, this exact same shape is going to reflect to there, and you would get the exact same shape. Okay, the exact same shape. Hence why you don't see a new curve drawn there. Okay, so you can take my word for it there that there is a reflection across the y-axis. So let's summarize. If the absolute value of k is greater than 1, the graph is horizontally compressed by a factor not of exactly the k value you see, but the reciprocal of k. So let's say the number was 3. So y equals cos of 3 times x. What's actually happening is a compression of 1/3. So by a factor of 1 over k. So whatever your k is, you take the reciprocal of it. That's essentially what's happening here. So if you have y equals cos of 3 times x, what's actually happening is a horizontal compression by a factor of 1 over k, which in this case is 3. That's your k value. All right? If you're between 0 and 1, you get a horizontal stretch. So it's still always horizontal because it's dealing only with your x values, not with your y's. Otherwise, it'd be vertical. And still the reciprocal. Okay, still the reciprocal. So let's say you had an equation of y equals cos of 1/3 x, 1/3 times x. Take the reciprocal. That's all that means. 1 over k, like 1 over 1/3 just equals 3. Okay, why is that? Well, because 1 divided by 1/3 becomes 1 times 3 over 1, which is just 3. Okay, that's just some quick math there. So you still do the reciprocal and you still plug in your k. So in this case, if your k is 1/3, you would have 1 over 1/3. But I mean, we just know that it's going to be 3. Okay, you've just got to remember that the reciprocal of 1/3 is just 3. Okay. And then lastly, if k is less than 0, the graph is reflected, this time across the y-axis. And that's why we saw the exact same curve, because it's just continuing on with the same curve. Whereas when it's reflected across the x-axis, you can actually see that the positive parts became negative and vice versa. Okay, so for the following functions, A represents the vertical stretch / compression. Also represents the amplitude, and it affects your y values, whereas k represents the horizontal stretch compression, okay, and it actually affects your period, changes your period. If your period was 360 and now your k value is 2, your period is going to be multiplied by 1/2. Okay? The sign of A represents a reflection, the sign of A and K. All right. So one thing to note before we end this video and we move on to part 2, that the period can be found using this formula. All you ever need to know is the K value, and you can figure out the period. And that makes sense, because let's think of the example that we had in y equals sine of 2 times x. So our K value was 2. And we found out that, our period actually went from 360 to 180 for that graph when our K value was 2. And let's prove why. 360, so period equals 360 divided by K. Look at that. You got your 180, which we proved on our graph that is true. Our period for y equals sine of 2 times x is now 180. It's 1/2 of what it used to be. Okay? And we can finish this video off here. And then I'm going to do 2 more examples in a part 2 of this video. Okay, so let's finish this quick. It says to determine the value of k, then state the period of each function. No problem. So we know that period is 360 divided by k. What's our k value here? it's 3, right? Because it's in this format. Okay? So we get P equals 360 divided by 3, which in this case, our period would equal 120 degrees. It got compressed horizontally by a factor of 1/3. The period used to be 360. Now it's divided by 3. It's compressed by a factor of 1/3. Here, our K is 1/2. Period equals 360. And instead of using 1/2 here, although you could, I mean, let's just change it to 0.5. But you could use 1/2. Okay? 360 divided by 0.5 is actually the same as multiplying by 2. So it's 720. So our period, and we prove this like above. We prove this in our graphs above. All right? And now here's a new one where K is 1/4. And we're going to do P equals 360 divided by 1/4, or 0.25. Basically, the same as dividing by 1/4 is multiplying by 4. So 360 times 4 is 1440. So now, for this, when K is 1/4, we're getting a horizontal stretch by a factor of 4. Our period is getting 4 times larger. 4 times larger. Okay? Let's stop the video there. We're going to do part 2 to this, where I'm going to graph 2 equations.